He is a research scientist at the Center for Space Physics, Boston University, and he is currently visiting LASP, hosted by Professor Lauren Blum. He got his PhD at the Astronomy Department, Boston University, with dissertation focused on nonlinear wave-particle interaction, and continued to work with Professor Wen Li's group afterwards. His current research focuses on both development of global kinetic model that incorporate nonlinear interactions and the energy electron precipitation driven by various plasma waves. So let's welcome Dr. Gang.
Hi, Jenny. Thanks for the very nice introduction for this talk. So today I'll be talking about the energetic electron precipitation into the Earth's atmosphere, driven mostly by Whistler mode waves. And I will also talk about the potential roles of nonlinear interactions in driving these electron precipitation. So very quick, brief introduction on the background. We are looking at the Earth's radiation belts, where it consists of energetic electrons that's confined by the intrinsic dipole or dipole-ish magnetic field lines. And you can see in the cartoon that these electrons go through the gyro motions around the field line, the mirroring motions along the field line back and forth between the mirror points, and the drift motion that's around the Earth. And then the pitch angle is the angle between the electron velocity vector and the background magnetic field. And whenever this angle is small enough, in the sense that it's smaller than a loss cone value, these electrons will be able to follow the magnetic field lines deep enough into the Earth's upper atmosphere, which leads to the precipitation that we will be discussing today. And of course, the other focus of this talk is the wave-particle interaction, which is a very crucial mechanism of scattering these electron pitch angles into smaller values within the loss cone and driving the subsequent precipitation. So there are two types. Before we go on, we can continue to look at the resonant wave-particle interactions and driving the pitch angle scattering. So whenever the Doppler shifted frequency of the wave is the integral number of the electron gyro frequency, as is shown on the cartoon, you can see the gyration motion of the electron is in phase with the perpendicular vector of the wave, and then that allows the energy exchange and as well as the pitch angle scattering of the electrons. So many types of waves, of course, can drive this resonant interaction, and our focus today is marked by these two bolded words, the Whistler mode chorus waves and the lightning-generated Whistler mode waves. So the first introduction on chorus wave is, which is a right-hand polarized electromagnetic wave that's usually generated at the magnetic equator. They are actually coherent and commonly observed with some very large amplitudes. The other interesting feature characteristic of the chorus wave is actually shown by this spectrogram right here, which is frequency versus the time, and the color bar is the magnetic density. And you can see that they show the chorus wave is marked by these rising tone, and in other cases falling tone feature, which with very discrete elements repeating one after each other. So these chorus wave elements, they can propagate along the magnetic field line, or they can propagate very highly oblique relative to the magnetic field line.
What causes the waves?
So these waves are generated by the electron temperature anisotropy near the equator, and then that leads to the subsequent Whistler mode chorus waves. So the other type of wave, which is also very interesting, is the lightning-generated Whistlers. So as indicated by the name itself, it's generated by lightning emissions within the Earth's atmosphere. And in some cases, these generated emissions can be leaked into the magnetic field line when they travel across the ionosphere, and then that leads to different propagation paths, as is indicated by the figure right here. So if there's a flux tube, so ducted density along the magnetic field line, these lightning-generated Whistlers can follow the flux tube to propagate from one hemisphere all the way to the other, while remaining mostly parallel to the magnetic field. And in other cases, they can propagate again obliquely relative to the magnetic field line, and then after this propagation, they can also mirror back and forth in the magnetosphere. So you see this back and forth mirroring motion, which allows the propagation to a different L shell, indicated in this cartoon. So the initial emission that is generated by the lightning close to it is this what we call spherics. It's this broadband, very bursty, short duration feature that you see right here. And because this frequency coverage is very large, it's covered from several hundred hertz to almost 10K hertz. During the propagation, their dispersion will become very significant, as is shown in the later by the Whistler, which is this hook-shaped falling tone feature that you see in this figure. So that's the more typical type of lightning generated whistlers that we will be able to observe in the magnetosphere, because you won't be able to observe it close to the emission, but it goes through some propagation time. So yeah, so these are the two waves that we'll be focusing on. And
why is it easier on the night side to generate whistlers than day side?
Well, mostly because night side ionosphere has lower density, and then it's easier for it to leak through the ionosphere into the magnetosphere. But there are observations on the day side, with just mostly on statistically weaker amplitudes. Yeah, so on this slide, I will just show a brief illustration on how these Whistler mode waves can drive the electron precipitation. So you see the orange line on the right is very out of shape Earth's magnetic field line. But wave particle interactions can occur in the radiation belts, which is marked by that box right there. And that pitch angle scatters the electrons closer to the field line. So it follows this magnetic field line all the way down to the atmosphere, which is around 100 kilometers in height. And then that leads to the collision between the energetic electrons with the neutral atmospheric particles. So that creates the precipitation. And in this same process, we can generate some other phenomena that you can observe, one of which is the Bremsstrahlung X-ray. So balloons such as Barrow at lower altitude will be able to capture these X-rays, and they observe, which is shown on the left. One of the well-known feature for this precipitation is called the microburst. So these are bursty precipitation, and in this case, it's X-ray, as you can see here, with a timescale fluctuating of 100 milliseconds. So these are very rapid, intense electron precipitation. So other features driven by, for example, Chorus wave includes the diffusive and pulsating aurora. So all kinds of features can be observed even within the atmosphere that's driven by the electron precipitation. So before we continue, I would like to introduce a very specific type of microbursts, which is called the bouncing packets. So these are microbursts, which has a very specific feature. So if you take a look at the peaks of these bursting precipitation, you see a very regular pattern. The peaks has almost the same spacing between each other. So these spacings matches the period of electron bounce motion. So is there a full bounce or half bounce of the electron adiabatic bounce motion within the magnetosphere? So these bouncing packets are previously known to be driven by the two waves that I just introduced, the Whistler mode Chorus waves. The example is shown on the left. This is observed by a low Earth orbiting CubeSat Firebird. And on the right is an earlier observation of bouncing packets by Volzatel in 1989. And that's driven by the lightning generated whistlers. So previous studies have actually reviewed some of the driving mechanisms for these bouncing packets, which is unique. So the initial peak is driven by the wave particle interactions that I mentioned earlier. But after the generation of the initial peak, the wave particle interaction actually somehow stops. And then the subsequent peaks that we see are due to the adiabatic bounce motion of these bunch particle packets back and forth along the magnetic field line. So that is why it is previously believed that these peaks, as you see in that figure with very clear features, they should always decay in time, because there's no external mechanisms that drives the additional electron precipitation into the loss cone. So they should always decay, at least based on previous understandings.
So why do you think the wave particle interaction stops?
Yeah, that's a good question. So actually, this is mostly based on this paper by Chen et al. 2020. They run a simulation on how you can generate these bouncing packets. Essentially, the first peak is driven by a standalone crosswave element,
Mhm.
and then in their simulation, they input only one element. So there's no repeating crosswave element.
Mhm.
So it's stopped because there's no waves. It doesn't, well, as I will show later, it's probably not always the case, especially in the case of lightning generated whispers. Yeah, but previous understanding, I think, is mostly like this. So what motivates the many of the wave particle interaction and precipitation studies? Well, lots of reasons. For one thing, this is very critical loss mechanism for the Earth's radiation belt. It can deplete the radiation belt very rapidly. Other cases, they also have important atmospheric effects to some extent. They can generate excess NOx and HOX. And recently, there is some ongoing study on the X-rays generated by these precipitation, which might be potentially hazardous to the high altitude and high latitude airlines crew members. So with that said, the main objective of this presentation is twofold. The first one is to understand the temporal profiles of the wave-driven precipitation, including microbursts. And second is the try to quantify the effects of nonlinear interaction, which I'll explain more later on in this talk. So before we jump into some of the results, I would actually first like to introduce how you can identify the precipitating microbursts. So a little bit of background. A lot of these previous results that I showed are current observations made for these electron precipitation is made by the lowest orbiting CubeSat or satellite, which is marked by this symbol right here. And even though their altitude is low enough, it's still several hundred kilometers. So it's sitting above what we like to believe the atmospheric boundary at around 100 kilometers. So in this case, you can see that there's a gap between the boundary and the satellite observation. So it will observe, as indicated by the middle panel, simultaneously actual precipitation, which is so this is the pitch angle, this is the flux or phase density, and the dashed line is the loss cone angle. So you see those electrons within the loss cone angle are actual precipitation. The electrons outside the loss cone angle, which still will be captured by satellite, are actually still trapped. So it observe a mixture of trapped and precipitation. But sometimes a lot of these CubeSats, they don't have a high enough pitch angle resolution. So we are not really able to distinguish based on the pitch angle what is going to be precipitated, what is going to be trapped. So one method that we apply is the O'Brien algorithm. The algorithm itself is essentially trying to distinguish between the bursty feature and the smooth feature, which is shown by the figure on the left. So you see by running this algorithm, we'll be able to identify the burst feature, which is the red line, and the smooth feature, which is the black lines. And because we know that these microburst flux are often driven by bursty waves, so we like to believe that these bursty features are wave-driven precipitation, and the rest is some kind of a trap population. So we don't take them into account of the total precipitation. And that's why we now like to show these recent, or not recent, but these barrel observations. So as I mentioned earlier, barrel is this balloon observation sitting at a very low altitude of around 35 kilometers, and it's observing X-rays that's produced by precipitation. So it only observes precipitation, it doesn't observe trapped electrons. And in these observations, based on some recent published studies by Cantwell and Millen, 2025, you can see that they observe microburst events, which I introduced earlier are electron intense precipitation, but they observe alongside these bursty component marked by the cyan color, you see this smooth component sitting at the bottom of it. So it's basically observing a microburst event that has both bursty component and smooth component. So this is different from the previous assumption that smooth component are crab population. They are also observed in these precipitation events. And after the statistical study by Barrow, it shows that these smooth component actually contributes a major portion to the total precipitation in these events. Sometimes it takes 70%, in other times it can even contribute about 90% of the total precipitation. So this not only indicates that removing the smooth component from satellite observation could underestimate the precipitation. It's also interesting thinking for us what mechanism can simultaneously drive the burst component and the smooth component. So that's going to be discussed first in this slide. So one of the mechanisms that we find is the time of flight effects, which can drive a smooth component simultaneously with a burst component. So I will first introduce what this is. So if we have a satellite sitting at the lowest orbit, or like Barrow sitting at a lower altitude, but at a fixed point, the timing of that satellite or spacecraft to observe an electron precipitation is determined by three components: the TF, which is the time for a certain frequency component within a wave packet to generate at the equator, and T wave, the time for that frequency component to propagate to the resonance location, and T electron, the time for the subsequent propagation of electron to observation site. So by combining these three components, we will not only be able to predict the timing of precipitation pattern, but we also notice, you can also notice that this final precipitation pattern is going to last longer than the wave that's driving it at the equator, because there's the other component that's contributing to the precipitation pattern. So which is why we show this, you see these results in the bottom panels right here. So on the right, I'm showing a very crude model of a coarse wave element. So it's a linearly increasing frequency lasting only a fraction of a second. And then on the left, you're seeing the precipitation that it will drive if you have a lowest orbiting satellite. So you see that the pattern is actually quite different because of this time of flight effects. And now if you have a repeating cross wave elements, then you see a repeating precipitation pattern. But what if these discrete elements are somehow closer? You might generate an overlapping precipitation pattern, and that will lead to
Question.
Yep.
What determines the width on the upper left there?
This one.
Yes. What determines the width? It's variable.
Mm-hmm. Yeah. So the width. So in the case of coarse wave, it differs from different waves, but it's simultaneously determined by these three factors. So the different energy dependent, it might be due to the electron propagation time, for example, because lower energies, they propagate differently. The higher energies, and then the different frequency component that a certain energy can resonate with, and of course the different frequency component have different propagation time. So I think it's hard to say what might overall determine the overall width. But in the case of lightning, I would actually explain it later. It's mostly determined by the propagation time because it's at a very different environment compared to coarse.
Okay.
But if we have like I said, repeating coarse wave element that's close enough, we will have overlapping precipitation pattern. And this is what you see right here. So in this case, we run a test particle simulation, and the result is shown on the left. So you see that these bursty components, they are due to the repeating burst of coarse wave emissions that we input into the simulation. The separation time is half a second, but the coarse wave duration itself is actually smaller. So there is not a continuous wave component in the simulation. But even though the wave remains discrete, you can see that at certain energy ranges, the precipitation pattern overlaps. So that creates a smooth component as well as the burst component in the simulation. And now for observations like Barrow or, for example, SAMPAX, they observe an integrated energy channel. So not only will they observe these continuous components due to the overlap, but if you integrate over a certain energy range. For example, in the case of barrel, it's about tens of keV to even higher energies. The result is shown on the right. So now you will be able to create a very substantial smooth component that actually is precipitation. So in this simulation, by just running a very simplified simulation settings, we are actually able to sort of reproduce what Barrow observed. The smooth component contributes about 60% of the total precipitation. So this, from the simulation side, also confirmed the fact that even with bursty or discrete wave settings, smooth component actually contributes to the precipitation. So by just removing them, you might underrest a large portion of it. And now we are going to jump to the case of lightning generated whistler, which brings this time of flight or TOF effects to an even larger extreme. So this is a very simple settings in our simulation, and I will explain this first. So we are assuming a ducted propagation lightning generated whistler. So they are generated at within the atmosphere here in the northern footprint, and they are going to follow all the way the field line all the way to the southern hemisphere, and that stops there. That's the very simple setting in our simulation. And LGWs, they are more favored in the inner belt, so we are assuming an L shell of 2 in this simulation setting. And then on the left is the dispersion that will be generated from just this propagation within the inner belt. And you can see that the initial spheric is marked by this vertical line. Oh, and the different panels is just different density settings. So the lower panel has higher densities, and the top panel is based on the statistical density model in the inner belt. So you see that the initial spheric is very short in duration. It's actually only 0.1 second in our setting, and the frequency coverage is large. But after the propagation to different latitudes that's marked by these different points, you see that the dispersion, it becomes very, very large. And then now if you look at, for example, at lambda 5, the duration of the lightning generated whistlers now extends to several seconds. In the lower panel, actually, almost 5 seconds. And it's mainly due to this propagation timing difference. And so even though the initial duration is very, very short and bursty, the final wave itself is going to be very large. And that slow propagation is going to dominate the TOF calculation. If you allow me to go back, you notice there's this T wave there is going to be significantly larger than everything else, and it's going to increase the precipitation duration to a very large extent.
Why your atmosphere boundary is only 100? So does that mean lightning can only go that far?
You mean only at 100 kilometers in altitude? So this is the shall we say, a conventional setting in radiation belt precipitation. We assume that 100 kilometers, the atmospheric density is large enough, and all the energetic electron is lost to absorption boundary. Yeah, so in our simulation, we don't go anywhere below 100 kilometers. We're just focusing on the magnetospheric wave particle interaction. And now, so this kind of TOF effects will be translated into the precipitation temporal profile. So it actually also is observed by another satellite, the SAMPEX observation in earlier years. So I'm showing you the examples right here. So the lower panel, you're looking at SAMPEX observations of precipitation above 1 MeV. And you see these regular space peaks, which is the bouncing packet, the characteristic of the bouncing packets that I introduced earlier. So the spacing between each of these peaks matches the electron bounce period at around L2, which is where they made these observations. But the interesting feature that we see in these panels is that the shapes of these bouncing packets is not what previous studies expected. It's not just decaying. So only the middle panel is showing a decaying all the way. But you also see this crown shape, which increases and decreases, increases first and decreases later. And you also see this flat shape that doesn't show any significant change in the precipitation flux. And by looking at the mapping footprint of these precipitation events, we'll be able to identify they are potentially driven by lightning generated whistlers. And the reason is shown on the left. So you see the precipitation footprint is this red dot here, and the conjugation point is a blue dot. So they're following the same field line. And you see the lightning discharge reported by Worldwide Lightning Network is somewhere close to that. So that indicates that these events are driven by lightning generated whistlers. But so what's interesting for the author who reported this event is that there's not a clear explanation on why we see these different shapes when previous simulations predict a decay, only a decaying shape of the bouncing packets. So this is actually due to the TOF that I just mentioned earlier, because the ducted lightning actually propagates very slowly. So that also creates a smooth component that's sitting below this burst component, and they are part of the precipitation, which is just excluded. As you can see here, the original observation is marked by this dashed lines, and you can see that the smooth component is just taken away directly. But in our simulation, by running ducted lightning generated whistlers that I showed earlier, we are able to generate these different precipitation patterns based on different combinations of inner radiation belt cold electron density or other parameters. But the bottom line is that you see a very large portion of the smooth component. And now if we are to follow the satellite steps, just remove this smooth component, you see eventually the shapes of these precipitation pattern is very similar. We are able to reproduce the crown, the decaying, and the flat shape that is observed by SAMPEX. But of course, as you can imagine, by removing these, we are still underestimating the precipitation flux in general. So that's a very extreme TOF effects from lightning generated whistlers that we observe and we are able to simulate.
Well, I'll ask this question now. We may get to it later, but then in previous estimates of the contribution of these bursts to, emptying the radiation belts, they must have gotten a smaller number, right? And so are you have you quantified how significant this, including the smooth component, is for doing that?
Yeah, thanks. It's a very good question. So from barrel observation, mostly the smooth component account for about 70 to 90% of when they observe a microburst event, for example, and it's quite frequent. In our simulation, we have not gone that far in testing all the parameters and simulate the potential range for that. But from observation, I can say about at least 70%. So the previous estimation might be like at least a factor of 2 different if we are to include this smooth contribution.
Okay, thank you.
Could you clarify? Well, understand, but I think you said you expect the previous understanding expect a descending shape for all components, but
Right.
both of your smooth and burst components are not descending your middle panel.
Yeah, so in the middle panel, it's not, it's a very complex shape, but previous expectations are for only the burst component. Because the previous expectation is that the waves, because it's discrete, they can only generate discrete components. So they only look at the discrete component and you see it's, in this case, it's always decreasing. But if we apply a more realistic scenario, for example, for lightning, we apply a statistical inner radiation belt density. And so that allows the slow propagation, and we apply a ducted propagation, which has been observed. We now have these other 2 shapes. But if we only have like a very short burst of wave emission in our simulation, we can only see this. So the conclusion from part 1 is actually mainly just even with just discrete waves in the inner magnetosphere, they can also simultaneously drive burst and smooth precipitation. And then so it will be very actually important to quantify how much amount do the smooth component contributes to the emptying of the radiation belt, for example. And now we can go to the second part, which is the effects of nonlinear interactions on precipitation. So in the previous part, all the simulations are quadilinear. So we use a quadilinear simulation to run everything to mix everything faster. But so before we go to nonlinear part, I was briefly introduce the quadilinear theory. The quadilinear theory, basically this right here is the electron energy versus magnetic latitude. So this is a very classic interaction picture between electrons and coarse waves. So the electrons is going to the right and then to the left, and the waves is going to the right. And at this location, there's a quadilinear diffusion, and you see the electron energy is scattered symmetrically to both directions. And the entire process is random, so it's a diffusive process. And by making these assumptions, we can simplify the Vlasov equation, kinetic equation, to a Fokker-Planck equation, and then you can make all sorts of predictions without heavy computation. So one thing you can predict is the electron phase density distribution versus pitch angle near the loss cone. So this is shown right here. So you see that the different colors are for different wave intensity, but overall the idea is that you can just use these two equations to calculate the pitch angle distribution near the loss cone. So precipitation afterwards without running the heavy computation simulation. So on the right, I'm showing the application by Ma et al. Can't remember which year, but of this prediction in the middle panel. So you can see that by using these prediction equations, we can generate, based on quadilinear models, the global distribution of the precipitation flux and also the precipitation ratio, which is a ratio between the precipitation and the trapped particles near the loss cone. So very convenient in application of quadilinear theory in precipitation. But now if there are some key assumptions of the quadilinear theory, which will break in many cases, one of which the most critical one is the wave amplitude. So if the wave amplitude is large enough, quadilinear theory will break. And more recent observations have shown that a lot of these Whistler mode waves that I mentioned earlier are actually strong enough to drive nonlinear interactions. So these are the nonlinear interactions that you would typically see. The top panel is the phase bunching. So when the waves and electrons resonate at this location, on top of the diffusion that you see in this final distribution, there's also a negative advection of the electron energy and pitch angle. So a combination of two processes in the phase bunching case. And now for the phase tracking, which is the second nonlinear interaction, after the initial resonance location, which is right here, that resonance continues for a longer time. So the electrons will be able to, in this process, gain energy from the wave all the time. So you see a very rapid acceleration of this phase trapped electron, and you see only an advection and there's no diffusion. So these non-interactions, they are not included in the current quadilinear model, and that's why we are interested in studying their effects. And previous studies have provided a very convenient way to identify whether or not you need to worry about these non-interactions, and that's the homogeneity ratio. So many versions have been developed, but I'm just putting one of them right here by Omura et al. 2007. So the intuitive understanding of that is this ratio is just the ratio between the magnetic field inhomogeneity. So how drastic the field bent versus the wave intensity. So the perturbation by the Whistler mode waves, for example. And whenever S is smaller than 1, we expect a nonlinear interaction to occur. Okay. What's going on? Okay. And then there's actually already applications of that inhomogeneity ratio in the statistical study of Vianam probes and SEMIS. So these are magnetosphere observations of Whistler mode coarse waves. So by plugging the observed wave parameters as well as other parameters into this equation, we can statistically analyze the probability for nonlinear interactions to occur in the radiation belt. And John et al. 2019 gave a very good results on that. So the color bar right here is the probability. So we only need to look at these 6 panels, and the color bar is indicating the probability for nonlinear interaction to occur. And the x-axis is the electron energy, y is the pitch angle. So you see that at the peak of these distributions, they reach about 30%. So actually a very often common occurrence for these nonlinear interactions. But what captures our attention for the electron precipitation is if you look at the small pitch angle regions in all these cases, it always predicts a close to zero probability. And that somehow is indicating that, yeah, in precipitation, you probably don't need to worry about nonlinear processes, which is actually misleading because these conventional inhomogeneity ratio are derived during the derivation. They make a assumption that the pitch angle is not too small. So they basically assume this region. And then whenever you get close to the loss cone, the conventional inhomogeneity is not going to work, which is why we see this black regions in these statistical results. Okay, yeah, so it's right here. Yeah, so so I somehow jumped a bit, but this. No, yeah, it actually somehow jumped a lot. But what happens when you get close to the loss cone, and when nonlinear interactions occur at with close to the loss cone, this is what you have. It's some very complicated processes which in combine we call them anomalous scattering. So they are a combination of trapping and bunching. But overall, the idea is that when the initial pitch angle, this is pitch angle on the y-axis, is small enough, after the resonance, their pitch angle will always be increased by the wave particle, nonlinear wave particle interaction. So if you have a quasi-linear, you will have a mixture of increase and decrease that allows the direct precipitation. But in nonlinear case, it always increases. So trapping increase more, bunching increase less, but you always, so that prevents the electrons close to the loss cone from direct precipitation, which is very different from previous quasi-linear model, which assumes that precipitation occurs close to the loss cone. And that the reason behind it is one term is somehow neglected, ignored in the earlier derivation of the nonlinear theory, but we are not going to get into those. But the idea is that there are some different processes that's not expected. And so that anomalous scattering non-interaction will then lead to this different picture of electron precipitation. So this illustration right here is for electron energy and pitch angle, and this is the loss cone. I didn't show it here, but if we are to apply a quasi-linear model, the precipitation scattering will only be considered along this loss cone angle. So it's a localized process. We don't need to worry about anywhere else for precipitation, for direct precipitation. But now if we consider a nonlinear model, we have a different picture. So this is a phase bunching boundary. So within this boundary, the conventional nonlinear theory fails. And that's when we have anomalous phase trapping, the positive phase bunching, that scatters electrons within this region outwards. And now where do we have our precipitation? From electrons outside this boundary. The phase bunching boundary, if you remember, will lead to a negative advection, and that will transport electrons all the way from high pitch angles to within the loss cone and creates a precipitation. So now we have an advective pattern instead of a diffusive pattern in the electron precipitation, and this very different scenario in the nonlinear dominant case. And that leads to different precipitation pattern, signature in electron pitch angle distribution and energy. So this is shown right here. The left panel is showing, for reference, the case of quasi-linear theory. So the solid line is the simulation. The dotted line is the quasi-linear expectations. So see that the simulation agrees very well with the theoretical prediction. And now if we increase the wave amplitude to 200 pt or 1 nanotesla, we see that the simulation is deviated from the quasi-linear prediction, first at lower energies and now at higher amplitudes is disagreeing with each other for the entire energy range of resonances. And now if we go to the flux ratio distribution versus energy, so it's this panel, you see again, the test particle and quasi-linear agrees when the amplitude is low, so that means quasi-linear dominant. And now for 200 pt, we see the disagreement at lower energy. And for 1 Tesla, it's the precipitation ratio is always lower compared to a quasi-linear prediction. So there's a lot of differences when we correctly treat the nonlinear precipitation. And this is only in the very idealized case. So these waves are idealized waves, and in reality, we need to include more fine structures of the Whistler mode waves. So that might lead to an even more different pattern. Okay. And now that we know that these nonlinear interaction can occur for small pitch angle regions, then the next question would be, so when do we need to worry about these nonlinear precipitation? And that requires, again, inhomogeneity ratio, but we need to rederive it because the previous one doesn't work. So this is what we do here. We rederive a new inhomogeneity ratio. So I will not explain the details of the whole derivation, but essentially we need to use a completely different framework for the analysis because the previous one assumption fails for small pitch angles. But the essential idea is that we can create this new T that correctly captures the nonlinear interaction at small pitch angles. So I'm showing some comparison with simulation results on the left. So you see that this is for 200 pt, this is for 1 Tesla, and it's again showing the T distribution versus energy, electron energy and pitch angle. So the bottom panel is showing simulation results. Essentially, the dark red region indicates where you have intense nonlinear interactions close to the loss point. And you can see that this dark red region is matching well with the blue region. The blue region is where T is smaller than 1. So T smaller than 1 always predicts, similar to a previous inhomogeneity, we chose to set T smaller than 1 for nonlinear regime. And so you see that the simulation matches well with the theoretical prediction. And now we can compare that to previous inhomogeneity ratio S. So the old inhomogeneity ratio by Omura et al., for example, in 2007 is showing the bottom panel, and this is for the wave amplitude in x-axis and the electron energy in y-axis. And now we show the T for which we derive in the top panel. And so both of these cases will require absolute value smaller than 1 for a nonlinear regime. And you can see that the new T now predicts a much larger region for nonlinear wave partial interaction compared to the previous S. So this new theory predicts a larger region, which again, going back to the statistical study, so we should, if we use the correct inhomogeneity ratio, we should expect some nonlinear interaction occur in the satellite observations, which is actually one of the next steps. So that's the conclusion for part 2, is that nonlinear electron precipitation drives a directed pattern different from the diffusive pattern. And these recently brought back to attention anomalous scattering processes actually creates a whole new mess in our analysis. And now we start to have more sense on how to correctly analyze these nonlinear interactions for precipitation. So that's the summary right here. I will leave it up. And I think the one takeaway is that there's still there are still major gaps in our understanding for wave-driven electron precipitation. And then so new studies, more studies are needed. And I'm happy to take any questions. Thank you.
Any questions for Longzhen?
A couple, but anybody else? So are the nonlinear interactions mainly occurring closer to the equator because that's where the wave power is greater? Is that right?
Yeah. So I agree that closer to the equator. Actually, let me go to this one. So closer to the equator, the homogeneity ratio is smaller. So we expect more intense non-interaction. So you can also see this pattern in the energy because the lower energy. In case of chorus wave, the lower energies corresponds to resonant location close to the equator. So you see that they're more significant at the low energy regions. So tens of keV in case of chorus electron interaction. But for 1 nanotesla, which yes, there are still observations of those, for example, chorus waves. It doesn't matter where the resonance is, we will always have nonlinear.
Yeah, but strong enough waves.
Yeah.
And then the other question is then, is the overall effect that this increases the precipitation relative to previous estimates?
Yeah, that's a good question. Thank you for asking that. So the short answer is we don't know yet. The current simulation would lead to the conclusion that it decreased the precipitation, but that's the idealized case. So the wave amplitude doesn't change, and so you will have only nonlinear interactions, and that's, I think, by now we can say that decreased. But in reality, we might have a mixture of local diffusion process precipitation plus the nonlinear precipitation. So overall, if that increases or makes it balance even, I think that needs more, at least for me, simulation studies to confirm.
Any question from people online or?
So for the lightning generated waves, is it does it have a location kind of preference? Is it more like mid high latitude, lightning happening in mid high latitude, or any such distribution?
Yeah, thanks for the question. So for lightning generated waves, I think the pattern follows the lightning strikes pattern. So for example, the North American continent is where you have a lot of lightning strikes, and that is also favored for the lightning generated whistlers. Now, if we move higher up to higher altitude, then we go back to the ionosphere dependencies, because it also depends on the ionosphere to block or let it pass into the magnetosphere. So there's also depend, for example, day-night asymmetry. That's due to the atmospheric effects.
Craig Rogers from New Zealand likes to pound the table and say, lightning loves land.
That's right.
And because of the distribution of land mass, it tends to occur more mid-latitude and so on.
I was wondering say if we agree it's over land, of course, it's a more lightning distribution over land, but the different latitude, does the effectiveness of those LGWs at different latitude?
Yeah, I would say it will have an effect. For example, so from a magnetosphere standpoint, if we shift to higher latitude, you map out further out to other L shells. So the mapping to different L shells decide. For example, in SAMPAX, this is for MEV electrons. So in the inner belt, there's really not enough MEV electrons for lightning generated whistlers to interact with, and then you don't really create these precipitation patterns, which is why I didn't really mention this pattern, but all of these events are observed in correspondence with a breach of energetic electrons into the inner belt. So in normal cases, you see that there's really not a lot, so they don't occur. These precipitation events don't occur. But in the case that they do, the high energy electrons do get in closer, then these mechanisms will start to create some differences. And also this one right here, you see, is along the point is along the North American land. So that's where the lightning strike occurs.
Sorry, what is that map showing?
So yeah, so this is showing the blue and red dot are the two footprints of the magnetic field line where SAMPAX observed these events. And then the yellow dot is the lightning strikes reported by Worldwide Lightning Network. So it's close to one of the footprints. That's why it leads us to believe that lightning generated whistlers are driving these precipitation events.
So then there will be also a seasonal. They will prefer the summer season.
If there's no further question, let's thank our speakers again. Thank you.